So welcome to Wireless Future Podcasts. So as usual, I'm here with Eric Larsson. But the unusual thing is, first of all, that this is episode 37 and the first time we are at the same place.
37 at the same place. Amazing indeed. I mean,
So the other unusual thing is that there are other people at the same place. So we have a panel here with 6 people that I will introduce in a moment. And then there is also an audience listening to this. So let me hear the audience. So the panel here consists of Lisbeth van der Her, that you have heard in previous episodes. And she is, for example, an expert on wireless Internet of Things, and she's from KU Leuven. Then we have Fredrik Tuveson from Lund University, working particularly with channel modeling and channel measurements and so on. We have Jakob Hoydis from NVIDIA, so working, for example, with what are you working on? I should read from a script here.
Anything related to machine learning.
Yeah, so machine learning for communication and software for that in particular. And then we have Dennis Gundus, also working with machine learning, but also semantic communication, source and channel coding and these type of things. We have Henk Wiemers, our sensing, localization and communication person. And finally, Luca Sanguinetti, a MIMO, holographic MIMO guy. So, since we have so many experts in the room, we wanted to take the opportunity to answer some of the questions that we have received from people listening to the podcast. We've asked around on social media, and things particularly that we might not be the best ones on answering ourselves. So therefore, the questions will go around to people here in the panel. So we will start then with Lisbeth. And so Internet of Things is something that you hear a lot about. We've heard about that for a long time. And it seems like the whole Narrowband IoT thing isn't really something that have become a commercial success yet, or has it? So I think my question is, where do we stand with connectivity for IoT, and what will happen soon?
Well, I don't have a crystal ball, but I think for Narrowband IoT specifically, I think the good thing is it could be implemented more or less as a software upgrade in the network, which made that the rollout is fantastic. From that point of view, if you would check the world map and where you have Narrowband IoT, that's really impressive. But it has, according to me, the specs have not been driven by application requirements or an economic requirement, and so it's for a lot of IoT cases, it's both requiring too much energy of the devices and it's too much money, it's too expensive. But what might happen, maybe can happen, is that if there comes what they typically call a killer application, and for example, think about the energy transition we have, the transition towards electric cars. If we want to couple cars with solar production and home batteries and all these kind of things, that might be a case where we need the data and where Narrowband IoT could be the exact solution that is fitting that kind of application, where it's not too expensive, it's not too energy hungry, and it can solve a puzzle, I think, that nobody has solved so far. So if there's some killer applications that fit with the specs of Narrowband IoT, I think it could become a success. And on the other hand, I think IoT is happening in a lot of bottom-up situations. Bluetooth Low Energy is there with longer range, LoRa networks are being deployed. So I think there's a lot of bottom-up things happening. But the top-down Narrowband IoT, I think if there's this kind of application that can really benefit from it, and that has an economic value, and it's a killer app in the sense that if you don't load your car, the car is dead, then I think it could make a big success.
So just for the benefit of myself and the audience, so Narrowband IoT is something like 15 kilohertz wide of spectrum. Is that correct? No. Or how wide it is? And what bit rates can you get? And how is the coverage if you compare to like standard cellular coverage?
The bandwidth is 180 kilohertz, so it's wider. the throughput depends on which kind of devices, but the coverage is even better than normal cellular. For example, it has a bit of strange skewed modulation technique. So, for example, in underground garage, it's better than normal cellular coverage. So it's everywhere normally where you have a cellular coverage and even better. So the robustness is a bit higher, and the throughput is definitely maybe not for high-end cameras all the time, but for a lot of higher-end IoT applications, it's even on the larger side.
So you got 180 kilohertz, which means a couple of hundred kilobits per second order of magnitude, and coverage even larger than the standard cellular. So when you're on the train, for example, between any major cities in Sweden, and one of the major, let's say, problems if you try to talk on the phone is that the coverage is spotty at best, but the narrowband IoT would still be available. So?
Yeah, but don't count on the few hundred kilobits per second, because it's very low in spectral efficiency. Yeah. But it should be better. One of the main unfortunate things is that, for example, roaming is not well supported yet. So for people working in logistics that could be very interested in using narrowband IoT, the roaming is not as we have with other standards. So saying I put it in a container and I will know where my container is, logistically from a number of non-technical parts, it's still very complicated. So that's also, I think, a couple of things to be resolved.
So are there some other use cases you believe will be coming in the future?
I think that the logistics is one of those use cases. There's a lot of even full containers getting lost.
Right.
And so I think in logistics we see lots of potential use cases. There, solving a number of these roaming issues and so on, I think is important.
Yeah, that sounds exciting. So one thing with this narrowband IoT, I think, is the question as to how much of power supply you will need at the device side. So there is a vision here that we could build like small devices that either live on a battery that lasts for a very long time, like, I don't know, a year or 2 years or 5 years or 10 years even, I heard being discussed. So there's a vision we can build these devices either relying on a battery that basically never dies, to the point that these devices would harvest power from somewhere, be that solar maybe, or from vibrations, or even from the RF itself. So maybe, Lisbeth, you could comment on like how we see the evolution in the future of devices that don't rely on an external power source, or don't rely on a battery that needs to be actively charged by somebody actually plugging it in, or be replaced during the lifetime of the device.
Yeah, I think also there's been some oversimplifications in some papers claiming what narrowband can do on one battery, because they forget a lot of things that are important, like the self-discharge and so on. I think if you can afford a solar panel and there is some sun around now and then it's amazing what you can do. If you don't have that, then you're very limited. If you need to live from vibrations, unless you're on a train or on the wheel of a car, then you have lots of vibrations, it can work, but otherwise it's very inefficient. RF power is very inefficient unless you use large arrays, and it's a few meters you can do. But if not, it's very inefficient in terms of 0.0 whatever percent. I think another solution that we are investigating now and exploring, and it's fun to do, is whether you can fly in a drone to recharge things on the spot. And then you can do something which is actually much more efficient than what you do with radio waves, to be honest.
Yeah, it seems like this could be one of the really annoying things with the IoT, that we will have many more IoT devices in the future than we have humans, and then they have batteries that run out all the time. Well, just going around and changing this battery will be sort of killing the whole thing.
Yeah, but also, I mean, if you're on board a vehicle, like you said, a car or a train, then there will be a power supply. Yeah? So the real question, I think, is if you mount these devices out somewhere in the field, or an agricultural field, or crop field somewhere, or in the forest, or maybe on board some animal could carry, like every cow could carry its own narrowband IoT device, signaling constantly how much milk is ready to be how to say could be I lost the word get from the cow or how hungry is the cow. Then this becomes a real issue, and then maybe a small solar panel, but of course then you would need a battery that you charge, and that would be depleted at night and so forth. So what are really like, or what is your vision here, Lisbeth, in terms of all these technologies? If it would look like maybe 10 years down the road, or I don't know, 20 years, will we see every cow out in a great saying out there with a Narrowband IoT on it, and a small sensor with Narrowband IoT next to every carrot or potato crop, or where do you think the scaling of this is heading, and where will it stop?
I think we may see a lot of things, but probably not with Narrowband IoT. I think there are other, and for example, if you think about crops, we're working on something which is a sensor for tomato plants and greenhouses. We now put there Bluetooth, low energy, and LoRa, but we think we will be able to do everything with Bluetooth.
Yeah.
So, and then you don't need to go to a cellular network. You can solve things much more locally. I think this open bottom-up networks and the fact that you can do this without, I'm sorry for the operators, without the whole big network, but solve the thing locally. I think there's a lot of great fun things to do. Even just building multi-hub networks between sensors, you can get a long way in woods and so on, without necessarily needing to go to something which is a bit heavy. I think for the extreme explosion of devices, I think Narrowband IoT is a bit overkill.
For free-range chickens, maybe.
Yeah, for free-range chickens, yeah. So maybe we just need to separate the issues here, right? So one question is what Narrowband IoT is and what it could be used for. The other question is building energy, small passive devices that rely on harvesting or solar or vibrations or even RF or something else, and how they could communicate and interact. These are really two separate maybe questions, because for the cows out in the field or the carrot plant, you wouldn't need these 180 kilohertz even. You would just need one bit to tell it's time to tap the milk, and one bit to tell that the cow or the chicken is hungry, and that would go along with a lot less maybe of frequency spectrum. So good, okay.
So is there anyone else in the panel who have any input on the IoT discussion? Or should we move on to
maybe
some better questions?
Some better questions, yes. So where do we go next, Emil?
I was planning to ask Frederick a little bit, since you have been looking into different kinds of frequency spectrum, for example. So one of the things we talk a lot about when it comes to 16 networks is the sub-terahertz band. So what is the sub-terahertz band?
I mean, sub-terahertz, typically we refer to things above 100 gigahertz, even though strictly speaking, it's starting a little bit further up. But say it's 100 gigahertz and above. And there we really have the other extreme compared to Narrowband IoT. I mean, here we are going extremely broadband. That is why we want to be there, because there is one of the few places where we really can get the bandwidth that we need when we have requirements for extreme data rates. So there, I mean, it's not sending 1 bit a day or 1 bit an hour. It's about, how do we get terabits per second throughput?
Right. So, and the fact that we are not calling it millimeter waves, is it because we are expecting them to behave rather differently than millimeter wave systems?
Yeah, millimeter wave and sub-terahertz, they are neighbors. So they have similarities. I would say the big difference comes when you go, 30 gigahertz and upwards. But then it becomes more and more pronounced the higher you go. And to an extreme, compare it to light. Extreme high upper terahertz. Take a torch. Whatever where you're pointing a torch, there is where you have a signal. And that is, we're getting closer and closer to that when we go up in frequency.
Right. And then at some point radio frequencies they start to bounce up and go around corners and things like this. So where did these effects really come important?
Yeah, I mean, so that effect we have somewhere, I mean, below 715, below 30 we can say. I mean, then you can start to have diffraction around corners so that we can go around corners. Otherwise, we have to rely on bounces and scattering. And so that is the two main propagation phenomena that we can use to get some coverage and to get non-line of sight links at all.
So from some kind of channel modeling perspective, is there something new we should know about these sub-terahertz bands?
One important thing is that since we need to have a large aperture still at the antenna side, which means that at those frequencies, since the wavelength is so short, it means that we need to have many antenna elements there. And when we have many antenna elements, we have directivity in our antenna. So we cannot have this omnidirectional coverage anymore. We can still have, I mean, decent coverage, but in certain directions. So we need to be able to find out where should we aim our antenna and where is the user moving so that we can track the user movement with our beamforming antenna.
Yeah, so basically you're saying that we need to build up aperture in order to maintain the length budget, but once you build up aperture, then you also get directivity.
Exactly. Yes, exactly. That is the case. So we need to maintain the aperture in order to capture enough signal. Otherwise, we don't have enough signal so that we can establish a good and reliable link.
An aperture here means the size of the array, or how do we define an aperture?
Yes, it's the physical size of the array, and then we put in our antenna elements in that physical size that we have available.
Yes, you also mentioned that is there some sort of like cutoff point at, you said, I think 30 gigahertz beyond which so beyond 30 gigahertz then the propagation starts to behave more like rays of light, like thinking of a flashlight, you just point around, you don't see a lot of diffraction around corners, and that really happens at 30 gigahertz. Did I get that right, Fredrik?
More or less. I mean, there is no strict line there that this, but I mean, it's happening there 20, 30 gigahertz somewhere, yes.
Yeah, so 20, 30 gigahertz, right. So, so then a question I think here is concerning modeling of the propagation. I mean, for visible light, we can rather well rely on ray tracing. And in fact, with ray tracing, we can generate photorealistic images of pretty much any environment today with the tools that we have available from computer graphics and so on. So when you work on modeling, and I know you worked on modeling of channels for basically your entire career, when we model terahertz channels, will we be able to rely on ray tracing tools similar to like what we do for just pictures with visual light, or do we still need stochastic models or fading distributions and that sort of things? Could you maybe shed some light on that?
I would say those ray tracing tools, they are very good in predicting what can we see and what can we not see. Yeah. So predicting shadowing, for example, that's okay, are we blocked or are we not blocked? The problem is when going up in frequency, especially at those frequencies, then we need also a resolution of the environment description in the order of millimeters and centimeters to do something reliable when it comes to the fine details of the channel.
So when you say fine details, and what scale are we talking here? I understand that the table, for example, here is tabletop is flat, and it's probably air quotes optically flat at terahertz, so that it behaves like a reflecting, the wavelength table has to be large enough, right? But you basically reflect the incoming wave. But if we take this another extreme, Jacob's sweater, that's kind of softish, then, and we illuminate, we illuminate Jacob here with 8 terahertz, would that be you need to know what quality of the wool in his sweater in order to properly model that ray tracing, or on what level of detail do you need to know the materials here, Fredrik?
Yeah, so there we are also, when we go up in frequency, go down in wavelength, a sweater, it's different if we look at the sweater at 120 gigahertz or if we look at it at 900 megahertz. Yeah. Because I mean, we don't, with the 900 megahertz, we don't see the details, and maybe it's Jacob that is acting as a good reflector or scattering object. But when we go up to 120, maybe this weather is absorbing everything, so we actually don't see Jacob anymore, because there is no reflection from there, because this weather is acting like a good absorber at those frequencies.
Yeah, I've been wondering a bit about this, because you see, if you want to go into the game of channel measurement, this type of thing, it seems to be less easy or harder and harder to sort of be relevant there. You need more antennas, you need expensive equipment to generate sub-terahertz signals and so on. So that's why maybe the easiest thing would just be to buy a better computer and run the ray tracers. So do you think we can sort of do a lot of propagation studies and things with ray tracing?
I think we can do a lot of studies with ray tracing, and we are actually doing it already today. But to do large-scale simulations and to get exact answers, I think we can have quite a good idea what coverage can we expect. But then, really, when going up in frequency, then we need a very detailed description of the environment, and that is typically not available today. Even if I scan it myself with the LiDAR, it's super hard to make a good model out of this LiDAR scan to put into my ray tracer. But still, for some certain points, I can do it.
Yeah, so we're basically returning to the point you need to know the material in more detail and not just its visual appearance in order to model how the terahertz wave is reflected or absorbed or not. Great. So, I don't know, how are we doing on time, boss?
So, is there anyone else who have some experience of working with terahertz? Or everyone is doing it just with the math? That's a simple way of dealing with things, right? So, when we were talking now about ray tracing, so I know that Jacob you have been implementing your own ray tracing software recently. How come?
Yeah, that's true. I did it. So the thing is, I have spent the last years working on machine learning for communications, and I felt that the real benefit of machine learning in our field will actually materialize once you let a system or model specialize to a particular environment. And that means you need to model a room or a part of a city as it is, and meaning you can't rely on channel models to represent this particular environment. And the only way we have available to actually generate channel impulse responses for a particular environment is ray tracing. We can, of course, do some measurements, but if you want to do simulation-based work, we need ray tracing. And since I work for a company that has a lot of experience in ray tracing for computer rendering, I thought, why not look into what they have been doing in the last 30 years as incredible advances there, and see if we can leverage this actually also for much lower frequencies. And that's why I learned ray tracing from scratch. I'm still learning, and yeah.
And it seems like that there were differentiable ray tracing, something that is happening there. So what can you differentiate in ray tracing?
Yeah, so essentially ray tracing is just, you implement a set of equations which are all differentiable, and now a differentiable ray tracer computes essentially gradients for you in an automated manner. That means, for example, you can ask a question: if I change the conductivity of one object a tiny bit, what will be the impact of my channel impulse response? And now essentially you can think about differentiable ray tracing as transforming a scene into a large system with many parameters, a bit like a neural network, and then you can start doing gradient descent on the trainable parameters of your scene to do something. And one of the things which I currently am interested in is precisely solving the problem of how do you get actually parameters of your environment. Meaning, as Frederick said, it's already challenging to get geometry, right? But I think that can be solved to some extent. So it's fairly easy to get a 3D mesh representation of the scene. It might look ugly, but you can get it. But the other ingredient you need for ray tracing is now, okay, all of these objects, what is it? What is the material? It looks like concrete, but maybe it's something else. And now with differential ray tracing, you can do measurement and calibrate essentially your entire scene so that it matches your measurements. So you can learn the things that you actually can't see.
Right. So if we put you in an anechoic chamber, we can figure out what the material properties are.
Yeah, sure. You could characterize Jakob at 3 gigahertz. No, but there's one thing which is there's a caveat. So typically ray tracing algorithms would like to have simple models because we need to look for specular paths. We need to construct paths that goes from one point to precisely another point. And if your scene is too complex, meaning you have very rough meshes, the algorithms to find these specular paths all will fail. And so we can't rely on this anymore. And I think so now for terahertz, maybe this is actually an advantage because specular reflection will be less prominent and we might rely more and more on diffuse scattering. For diffuse scattering, you don't need to find exact paths, you can rather connect essentially any reflecting point to a receiver. And that's then much more similar to what's done in computer graphics. And then we can leverage the full power of rendering algorithms actually in our field. So maybe it can be far more efficient for terahertz than for lower frequencies.
Right. Yeah, question?
Well, I mean, so it feels slightly like contradictory. You could actually differentiate a ray tracing model because if you think about it, you could be just right at the edge here. So I see that seat over there, I see the seat blocking it, and then I move just an epsilon to the right, and then one of the reflected rays will be totally blocked, which corresponds to something like a step function. If you think of just signals and systems terminology, we know that isn't differentiable. So how accurate, now I didn't have the chance, unfortunately, to come to your talk this afternoon, but how, maybe you gave the answer there, but how sensitive, I mean, are your models to that sort of phenomena?
Yeah, very good question. I think one needs to differentiate between differentiability with respect to, call it scene parameters, and actually the geometry. And scene parameters, that's easy, but computing gradients with respect to geometry is a much more difficult beast. Some people do it in computer rendering, it's possible, but you need to come up with heuristics for gradients and so on. It doesn't work so well. So I don't think we're at a point yet where this works in our field. But with respect to losing suddenly paths, I mean, we still have diffraction to some extent. And though you still get a field, it's never you lose something suddenly. But
yeah, sure. So that's reassuring to know, I think. So what do you think are these models going to be used for eventually? Now, suppose that we had a fully differentiable channel model based on ray tracing. What would you use that for? What is your vision here?
Yeah, so the big vision is, to some extent, I would like to take randomness out of communications. And the way you can do this is by predicting things, right? Because that's actually not randomness in communication. You just move around, you will know what the channel will look like, but it's not random. If I could perfectly predict it, there would be no randomness anymore. I could build infinitely reliable systems to some extent. And so one way of making communication system more predictable is by having better models to predict what's happening. So if you could construct essentially a real-time digital twin that would allow you to compute propagation conditions, you could probably do things much better. And the other thing is, I would like to use these models. If I have a very good digital twin, I could now start looking into what could a machine learning model actually optimize in such a scenario. Can I do better? Can I do better because I can now overfit to this specific environment? And to answer these questions, if they actually benefit in doing this, you need such a tool.
Yeah, I can certainly see there will be benefit. I mean, but how would you actually track how the environment evolves? Even you take, I mean, let's say you had this room here and I've got people like slightly moving around with their heads, which I think is a good sign because you guys seems you're all awake. But let's say I take my pen here and I move it a little bit. Now, retrain. I mean, you need either we have to be under constant surveillance in order to gather enough data for your ray tracing algorithm to compute its different derivatives, or you would need some sort of feedback mechanism, I suppose, from the actual terahertz link that tells the model that, hey, stop, something has changed here. How would this actually work?
Yeah, so that's still a bit far-fetched, but there are neural radiance fields, so-called nerves, Essentially, you take a few pictures, you would install a few cameras somewhere,
Yeah.
and they allow you actually to essentially create in real time a 3D model of your environment. And you could essentially film this and you train this in real time with 60 frames per second and you update your 3D model in real time. So I think that's possible. And now, if your ray tracing algorithm is fast enough, and I think we're getting there, because for computer graphics you can do real-time ray tracing, you would be able to actually solve in real time. You could update coverage maps in real time, even if your real-world changes. So we are not there yet, but I think that might be.
Wow, that's a cool vision. Yeah, amazing. Okay.
So, since you have been working a lot with machine learning for communication, one of the things you are known for is some kind of end-to-end learning or auto-encoder. So, do you think we in the future will replace some of our wireless protocols with learned protocols?
Yeah, I think actually Dennis is much more optimistic than myself.
Right. So we will soon go.
But the thing is, I kind of reached. I think I've pushed this field as far as I could, and I haven't discovered anything so far that cannot be learned. So you can even learn new waveforms that outperform what we do. But the thing is, the gains are not really large, and it's not just because you can do something, it's what you should do. And now, pragmatically speaking, if you want to convince anyone in 3GPP that this is the way to go, it will be very, very difficult. So what I think, a pragmatic thing, I hope is happening, is that we will see more and more machine learning enhanced algorithms, but that are standard agnostic, meaning you have some machine learning models, for example, in a 5G receiver. And that's already a very, very difficult thing to do. And that's one of the things I'm also looking into, actually proving that you can do, for example, neural network-based signal processing in real time, running on a 100 megahertz channel. Even if the performance is worse slightly than what we do, I just want to kind of show it can be done. And I think the first step, so to think even further into end-to-end learning or something like this, people must realize you can actually do it. And once neural networks are there and become mainstream, then maybe we can think about, hey, maybe you can learn things end-to-end. But I don't think it's going to happen in the 6G timeframe. So there's still research opportunities for 7G, I guess.
So should we hear another?
Now that, it was referred to. Yeah, I mean, I agree with the fact that I don't think this is going to happen very soon. I think the standardization, of course, is a great thing, of course, as we know, but it's also a block kind of to transform things very, kind of fundamentally. So in that sense, it's going to take time. But what Jakob was also saying, I agree with the fact that you can do everything pretty much better. And I think some gains in some applications, in some domains is significant. I think it's a matter of, when there will be real need for that. And I think, so right now the communication networks are mainly serving, us, mainly for content delivery. I think for those, we're maybe good enough. But as we move towards, new applications, as many people talk about, more maybe AI-oriented applications that might have different type of latency requirements and rate requirements, then maybe we will have more needs for this new type of algorithms.
So Luca, you have worked on this as well a bit, or?
Yeah, just a bit. I was using the demo Jacob
All right.
students, and actually I was surprised by what you can do with the end-to-end learning scheme. What was very fun, actually. Actually, when I was trying to use this platform, the students were also able to attack the network very quickly and let the receiver provide an output which was very much different from what expected. So that's why I was also wondering if this kind of system may be more vulnerable to attacks and try to push the neural network to give you a dog all the time when instead the future is a cat very easily.
Can I respond to that? Have your students tried to attack a normal system?
Yeah.
Because I think it's as easy as so on the physical layer you just jam something.
Yeah,
it's the same.
You just get nothing. Probably you don't get the image. The problem is that if you can attack the receiver in a way that instead of getting a dog, you always get a cat So that's the point. I mean, a normal system can give you nothing, an image that doesn't make any sense. Maybe the neural network can be tricked in a way that instead of delivering the cat, is going to deliver the dog. I don't know if this is the case, but
So yeah, I think you raised an important point, and I have no good answer to that. And that's it's and typically you have CRC checks that tell you have correctly received a packet. And now if we go towards this, say, more generative kind of type of communications that maybe Dennis will speak about, where it's not about you can't really say you have correctly received to a bit precision what you should have. Then you run into these issues. And if you have no mechanism anymore to tell you 0-bit errors, next packet, then you're kind of stuck. And also I don't know how to deal with encryption. Normally we have some type of encryption going on, and this would all go away. And but I have no answer, and think a lot of things to be done.
So talking about AI, so a lot of people talking about that, and it seems particularly in the 6G context, people are saying that 6G will be the first AI native technology. So what does that even mean to be AI native?
Okay, so I mean, I personally never used the term, but I've definitely seen it used a lot. So I think it's one of the, since it's not a mathematical definition, it's hard to say exactly what it is. Maybe everybody means a little bit different. But I think basically it covers everything that somehow, how we can incorporate AI into the, definition or the design of the next generation network. So somehow, and this involves, of course, what we were just talking about, using AI to design, new algorithms, maybe, encoder, decoder, waveforms, etc. But also, I think maybe in the more short term, enabling things like to allow the network, for example, just to collect data, right? So this may not even be for the sake of optimizing the network itself, but maybe it's for other kind of purposes you want to do for machine learning or anything for IoT type of devices, collect a lot of data, and that data has to be somehow efficiently collected, stored, processed across different types of networks, different type of vendors. So all these things should be somehow part of the design. So I think that's what what's meant, that the next generation networks should be both allow for us to use them for AI training or inference, and hopefully also should use AI to improve their performance.
Yeah, so I think I saw a talk somewhere where somebody suggested to use a chat GPT style, general AI in the context of wireless networks. I'm not quite sure I understood exactly how this is supposed to work, but one application case I could think of is that you got your system, you got all your access points and deployed, you got your whatever switches and cabling and all of this. Now you just talk to the system and say, hey, make sure to provide coverage right now, here and there, and especially there, and make sure to provide low latency, and make sure to provide this ultra reliability and so on, and the system just does it for you. Is that like the vision with this native or AI native, or is there something else here that I've been missing?
Okay, so I think, obviously, if we can just ask the network to give whatever kind of performance KPIs we have, and it provides, I think that would be great. But I don't think that has much to do with GPT. I don't see. So basically, whether we say it in English, the network, and I think that would be the minor part of it. So, whether that's capable of doing it or not.
Yeah, but I did speak to some folks in the industry who suggested that actually to configure all these systems, right? Because these mobile networks are enormously big systems with lots of components that we maybe don't all of us think about on a daily. We get the base stations and the towers and all of this, right? But then we got the whole core network and switches and operation centers that need to be configured with configuration files that are just unmanagedly large, and even here just being able to talk to the system rather than sitting and fiddling with parameters and tweaking the operation could be, let's not forget that aspect, right? We talked about this end-to-end thing where you could replace your turbo code with Jacob's learned algorithm, but maybe at higher levels there would be even more opportunity to actually leverage general AI to configure and run the systems.
I agree the fact that that the system is very complicated and it would be nice to simplify the optimization. But I think the challenge there, I don't know how much of the challenge, at least the part that's to really control it by, let's say, speaking in English rather than going and optimizing some parameters. I think right now, given the state of this large language models, I think that's probably solved, right? So that right now we have tools to convert what you say, what you want into parameters, but now the challenge is still there. How do we really optimize those in real time? So that I think that's a point where other AI tools, not necessarily ChatGPT type of tools, they might be very useful. So I mean, ChatGPT, as you know, is kind of this next word predictor in essence, right? So I don't see how it directly impacts. Of course, for anyone familiar with information theory, you can directly see that it's a tool to compress for compression, right? So because basically it gives you a very good model of your information source. So if you want to compress, for example, text in English, so now thanks to ChatGPT we have a very good probabilistic model, so we can design a code that's optimized for this model. So that can help us for, let's say, text compression. That's kind of obvious. But I think there's something more. So the core element of this type of tools is the transformer architecture. So that's a new kind of, now not the new maybe so much in the machine learning sense, but that architecture I think has potentials for to be used in various wireless network applications. So we have actually done things like designing codes for channel estimation, CSI feedback, things like that. So for many things that people have used other machine learning tools and got very good performance, I think pretty much always you can get better performance using transformer architecture.
So is this improvement big enough so it's sort of worth start to looking into actually using these things?
I think that's of course question. I don't know how big it should be for let's say to have a commercial application. And again, as I said, I think it will really depend on what type of applications, what type of requirements you have. But Jakob said also that I'm more optimistic. I think in the future somehow these tools will be used for maybe not in this very standardized mobile network kind of things. But think of it like this. Now we are talking about all these kind of ChatGPT agents and these are somehow getting smarter. Now, if we allow them, for example, to communicate with each other, so how are they going to communicate? Do you think that they're going to use our standardized mobile networks?
UPSK.
UPSK, exactly. So I think we should maybe now think about that. How would actually, if you allow some intelligent agents to establish some communication, among themselves, so what would it look like?
So is this related to what people call semantic communications?
I guess so. In a sense, again, these are very general terms that everybody might mean something else. I think semantic communication in general, from my perspective, means that when you transmit something, when you communicate something, you want to communicate the information that is the most relevant for the receiver, for whatever the receiver wants to do. So a good example would be, for example, if I want to send you an image, you might be interested in reconstructing this image with highest fidelity in terms of maybe the pixels. You want to be as close to original as possible, or you might just be happy to have a sketch of the image. Maybe there's just one person in it, a house, or you might just be, you might be happy with a textual description. So I think semantic communication is kind of a communication system that can deliver any of such requirements.
Right, so maybe the simplest version of that is how emojis look different in different platforms, but it's still supposed to be the same thing.
Yeah, you can say that.
So is there anyone else who have any input on our AI discussion?
A short one. Just a very short comment about what I think about AI native right now. So I think for me it means to actually enable, from a standardization point of view, the use of machine learning in future networks, because it's not really working in 5G. So nobody has access to data, especially on the physical layer. That's why nobody in the world actually shows real demos, because nobody has access to data. So NF native means you build a system, you make technological enablers in terms of message exchanges and so on that allow you to implement machine learning solutions. which you couldn't right now at the moment. And so that demystifies it a bit for me. Maybe I think some researchers have some more aspiring ideas, but I think from a pragmatic point of view, that's what's missing. And I think also the 3GPP study items, and I try exactly to do this, to think about what do we actually need to do so that machine learning can be implemented.
Is that a little bit taking edge computing to the next level? I mean, it was discussed a lot a couple of years ago. I mean, we should have edge cloud and we should put compute resources. And how are those ideas different from what we thought 5 years ago?
I don't know if I have a good answer, but I think what's definitely happening is that everybody wants to bring the power of large language models to the user device. And so either we put these models in the edge, but then there's still the communications bottleneck. But I actually think what's happening is that soon your smartphone and all devices will run them locally. And you see this already. There's so many companies trying to embed this. I wouldn't be surprised if some of the big telephone manufacturers will soon have dedicated LLM accelerators in there. So but I think there's still these large models that might be multimodal models and so on that should run on the edge. To at least give you the feeling that the intelligence is as close to you as possible.
Can you just make a philosophical, thinking here? So if I see what they have done in the machine learning community, there is one thing which is very common. So they have common data sets which are used to devise algorithms and to do comparisons, and they've been very successful just because of this. In our community, we want to have a native AA network. So we are not used to share data. We are not used to compare performance according to the same data. So in my life, I've never had the chance to get access to data and measurements or whatsoever. So do you think this is very much needed to make process in this direction, or we can just everyone using his data, his models or whatever, and then we come up with solutions which are not very much making any progress? I think this is missing in our community.
Yeah, so the thing is, I don't think that's what's missing. I think what's missing is a critical mass of people who work on the same problem. Like, thousands of researchers working on image classification. What we have thousands of researchers working on thousands of problems. Because we have so many problems, right?
Accurate.
And everybody does something, and I think we have never agreed upon this is this one important problem that we want to solve, and now let's try to solve this all under the same assumptions and, fight it out. Who wins? So that's, I think, what's missing.
Yeah, but will we even need data sets and measurements once we get your ray tracing tool, Jacob?
No. no, I think it's needed, would be needed. Real data can't be replaced. But I think we had also a great discussion in your podcast about reproducible research and so on. And so one of the reasons why I'm also very much engaged in open source tools and sharing all of the results is to have reproducibility and enable actually also this type of comparison. So my feeling is the data is always needed.
Yes, and data is always needed, but in order to make sense of the data, that is the problem. I mean, give me a hard drive and I will fill your hard drive in a minute with data. But it will take you a year to interpret what's there. And there we have the bottleneck. It's not the data itself, it's really, when we do measurement and look at the data and at the transmissions we have in our cellular networks. It's huge amounts. So in order to grasp what is really there, that I think is the key bottleneck.
Yeah, but my point is that if we don't have this common playground, we're just each of us is gonna play with his models, his data, whatever. So we are not making any progress in the direction that Jakob was mentioning. So we're just working, each of us, on different problems, different models, and then this is very much different from what the machine learning community has done for years and has been very successful in this.
Right, so with that, let's move on to the next problem. And Jess, let's ask some question to you, Hank. So when I was recently in discussion about setting up some big collaborations in Sweden and talking about wireless, I was told, don't say wireless communication, wireless is much more than that. And of course, we have also the localization sensing parts, which traditionally have been a number of different technologies that are not really integrated together. So if we compare this type of things, why are we using different systems? Do they really need different solutions?
So if you think about wireless communication, how it's different from wireless positioning, I think there's a change happening, but let me talk about that later. So if you think about your second favorite equation, your first favorite would be probably 1 plus SNR. Your second favorite equation is y is hx plus n, right? And then the difference is how we look at this equation, how I feel. So in communication, you care about x, and the h is just in the way. And in localization, we care about h, and the x is in the way. And that means typically we use pilots to estimate x, to estimate h. And then in communication, you care about this matrix h. You don't really care what's inside. Well, for localization and sensing, we care about the geometric information within this channel, the angles and the delays. Another way how localization is different from communication is we care about geometry. That means also we need several base stations to be localized. While for communication, you need only one base station to communicate. And I think originally these were two different fields, right? In localization, you had GPS, you had ultra-wideband, several other systems, but this is now converging, mainly due to the shift in 5G from FR1 to millimeter wave, where all of a sudden a lot of spectrum opened up, new signals were defined, a lot of progress there, and so now it will be one system that can do everything, maybe not for all applications.
So are we traditionally using different frequencies for this, or is just how we do the physical layer?
So the conventional positioning systems use different frequencies, but for instance, ultra-wideband, which is a very large bandwidth, but the underlying channel model, let's say, is the same. It's just a multi-path model where we try to extract the line of sight but to localize yourself. So from a positioning perspective, when you move from ultra-wideband or GPS to 4G, 5G, nothing really changes. It's a different waveform, slight changes in processing, but otherwise it's really the same.
Right. And now when we started to use a lot of antennas for wireless communications, are antenna arrays also used in positioning, for example?
To some extent in the Bluetooth positioning, but you really see, again, in the move to millimeter wave and also a massive MIMO, that you have really a large number of antennas with a large aperture, which allows you to get a very fine angle of arrival, angle of departure information. And this really augments the positioning system. And also provides additional ways of getting resolution, so ways of resolving multipath, even though when you, for instance, have limited bandwidth, but you have a lot of antennas, you can resolve the multipath and extract this precious line of sight that you care about.
Mm.
Yeah, I mean, we had large arrays much earlier for positioning and angle estimation within radar, for example, phased arrays many decades ago. So is my understanding correct that the new thing here is the integration of sensing and communications? And if so, what does the integration actually consist of? Is it to use the same signals for both purposes, or is it to use the same piece of hardware, or both? Maybe you could educate us a little bit on that.
Yeah, so I think if you ask 5 different people what is integration, integrated sensing communication, you will get 10 different answers. So my own view is that this integration can manifest itself in many ways. The integration could even be that you put cameras next to the base station, and then the information from the camera could inform the base station about how to improve communication. It could be that you reuse the same spectrum, sometimes for communication, sometimes for positioning or sensing, using separate devices. It could be that you use the same device with the same spectrum, sometimes for communication, sometimes for sensing. It could mean that you use the same waveform, sometimes for positioning, sometimes for sensing. And it could also be that in the extreme case that you do this concurrent transmissions for communication and sensing. But that's really just one extreme case of this broad spectrum of integration of communication and sensing.
Yeah, because I mean, speaking of using the same signals, isn't that quite natural? I mean, because both for communication and for sensing or positioning particularly. You want the right bandwidth. If you think about it, time of arrival estimation, you want a signal with a peaky autocorrelation, which means that it will have a flat spectrum in the frequency domain. So that's like equal or there's frequency content everywhere. Just like a signal designed for communications has. So isn't this like well known all along that you want to use signals that resemble white noise more or less, both for communications and for positioning, and then maybe also for sensing?
Right, so I slightly disagree. I agree that we want large bandwidth, but maybe we want to use the bandwidth in a different way.
Yeah.
There's different aspects to this. It's, for instance, the rate at which you do positioning and sensing is different to the rate at which you do communication. You don't need to communicate. You don't need to position devices every 10 microseconds. Secondly, in terms of the spectrum, I would argue for positioning, we don't want actually a flat spectrum. We want some kind of power allocation that gives more power to the boundaries of the spectrum. That's actually much better for positioning.
Yeah, that's actually true. I mean, technically, if you look at the camera bound for time of arrival estimation, then it will be, I think, inversely proportional to the effective bandwidth of the signal. So there is an advantage in putting more power towards the end of the spectrum. And that advantage will not be there for communications. So I obviously have to give you right on that. But I think the question still persists or remains. I mean, where is the main, or where is the novelty here really? Is that in integrating the sensing, the communication? Is it that you want to reuse the same piece of hardware for both purposes, or is it more, or is it something else?
I'm not sure how to answer that question. I think it's the drive comes, I think, in the first instance for improving the communication system itself, right? So you want to spend some resources, time, frequency, or spatial, to do sensing or position that can improve the communication. And then in addition, if you have this regime with large bandwidth and large antenna arrays, you could probably enable certain external systems, external services and applications that require very high precision, high integrity, or extreme coverage.
So the impression that I have is that people working with building sensing systems are not very impressed with the idea about merging these type of things, but I think from the other direction, so if sensing systems of today are mostly maybe phased array based, and then having a digital array for that is really high-tech military things, then in wireless communications, using digital arrays, everyone have that now in their 5G phone already, so building upon that and having that all over the place should at least be an add-on that can be used from that direction.
Yes, and I think this is just one of the many examples, right? A lot of the technologies that we're developing for communication have potentially never been thought about for positioning and sensing. There's the introduction of arrays, there's the use of AI we talked about, there's distributed MIMO where we could have phase coherent transmissions and carrier phase positioning. So there's lots of opportunities, I think, for improving positioning and sensing towards 6G.
I think a key aspect is that, I mean, we envision that the infrastructure will be there, and it's there for free, basically. So we can use this infrastructure for other purposes than just communication. And this is a key aspect, I think, when it comes to positioning. We don't have radar systems everywhere that is accessible, but we do have communication systems there.
So when you speak of integrated communication and sensing, you really mean that, well, now we got all this hardware, it's already there, all these MIMO arrays with all this digital processing and front ends, and then they can communicate, they can form beams and all of that. So why not just also use them for positioning applications or sensing applications? When the hardware is already there, the waveforms partly as well. Yeah, super. Okay, so maybe that might be a signal that we should move on, Emil.
Yeah, I think we should talk a little bit about MIMO as well.
MIMO.
We have Luca here.
Of course, Luca.
So you have been working with the holographic MIMO recently. So what does holographic MIMO really mean?
Okay, so as I said all the time, I mean, I think it's just a marketing term which we have been using for whatever it is beyond massive MIMO. But in general, the idea is that the lesson learned with massive MIMO is that the more antennas we have, the better, which was kind of known, but massive MIMO was like reinforcing the statement. So this holographic MIMO thing is basically within this trend. The idea is to have more antennas. You can deploy more antennas in space. I mean, for example, in this room, or you can even go for larger space like the campus, and then you have distributed MIMO, or like here, the extremely large antenna array aperture. The holographic MIMO thing is that if you give me some space, which is, let's say, constrained, not so large, what I can do? I mean, can I do better than just placing antennas in land over 2 and then exploring more the degrees of freedom, the channel? This is more or less the question that we're trying to answer. And yeah, it's not clear if there is any advantage if we go for classical implementation, but there is probably space for different antenna technology space. For example, metamaterials, metasurfaces, they may enable they may enable us to better exploit the electromagnetic channel given the aperture that we have.
Okay, so you have a given aperture, you have antennas inside of it, there is some spacing in between, and you add more antennas.
That's the classical way to densify the array. Otherwise, you can also think about these metamaterials, and then you have your digital signal processing behind the metasurface that is going to first process the electromagnetic channel in a way that's convenient for the digital processing unit. This has an advantage probably not in terms of performance, but in terms of complexity, power consumption, which is one of the limiting factor when you want to go up with the number of number of antennas, which means number of radio frequency chains. So we need to come out with different implementations which are equally good, but have lower complexity, lower power consumption, and can be implementable in an affordable way.
Yeah, so returning to the talk you gave here earlier in the afternoon, Luca, as if I understood well, one of the conclusions was that if you want to cover like an aperture with antennas, then lambda half spacing is kind of the optimal, all things considered. And then I was wondering, isn't this already well known? I mean, isn't there something like a theorem in electromagnetics stating something to the effect that you got a source, and no matter what the source looks like, it could be like an array or something. I mean, it shouldn't be like anything that exploits super directivity, but it's a bunch of antennas or anything that radiates. You got a source, and then you enclose this source with a sphere, and then you look at the field in spherical coordinates, you expand the field strength in spherical coordinates, and you look at the eigenvalues. Then they will like be kind of like constant like this almost, and then suddenly they fall off like a cliff. And that fall off a cliff happens when the number of eigenvalues is proportional to the surface area of the sphere divided by something like lambda squared. Which effectively implies that by placing antennas on the sphere with a wavelength or half a wavelength spacing, captures all the information that the field has in it. Could you comment on how that relates to like your conclusions from your talk earlier today?
Yeah, this is true actually, and if the aperture is very large, and then this is even more true, because I mean, what you're seeing is like the sampling theorem that we have in
Yeah. I mean, so I promised you I'd give you a hard time before we started the recording. But to me, this is like the sampling theory, right? So you got in the time domain analogy, it would be you have a narrowband signal with a bandwidth of P. We all know that if you sample with an Nyquist frequency twice the bandwidth, you capture all the information that's in the samples. And if you have white noise within this bandwidth, then you'll get uncorrelated, statistically uncorrelated noise samples. If you sample faster, you will not capture more information. You'll get more samples of the noise, but those noise samples become correlated. And so it's like same thing with the aperture. You fill your aperture with lambda half spacing of antennas. If you put the antennas closer, you're just going to get correlated measurements. You get no more information. So my counterpoint to like your talk here was that I obviously agree with everything you said, but I would maintain, isn't this already well known?
Okay, as I said, this is true as long as you have a large aperture rate. I totally agree with you. Like the sampling theory, this is true if you have a large time interval. if the signal is short, the sampling theory doesn't hold. Because the bandwidth is not finite.
Yeah, that's a fair point. I mean, so
we are
the
doing-
aperture has to be large enough here for these arguments to be valid. Just like for sampling a signal, we need large enough time window, right? I mean, the
We
BT
need a
product
finite
has to be large enough for the sampling theorem to deliver a reconstruction with a small error.
I mean, in communication system, we often are doing oversampling also in the time domain for various reasons, I guess, too.
Yeah, but
But by the way, the conclusion of my talk is in line with this observation. So if you have a short array, I mean, the aperture is not small compared to the wavelength, then having closely spaced antennas can give you some benefit. But if you have something which is large compared to the wavelength, which is precisely what we have in the sampling theory, then lambda over 2 is kind of optimal.
yeah. No, I mean, just to be clear on that point, I think we fundamentally both obviously agree here on the fact that the aperture has to be large enough for this our argument to be valid. So, I don't know, Emil.
Yeah, should we take a last?
Or you want to say something?
No, I think we should take the last question.
Well, I think there's a dinner waiting for us. Otherwise, we could keep on talking forever here, I think, about apertures and antenna spacing. And yeah.
But I think one thing that related to big MIMO or is the radiative near field that people are talking a lot about these days, at least people who still want to do MIMO research. So what is your view of that? Is this something that people are analyzing as basic research for curiosity reasons, or will it be somehow important in the future?
So just to your question, when you say radiative near field, then this is not really an array effect, right? I mean, the question would be like equally valid if you had just a single, whatever, dipole or something. We'll look at answers so that the context is clear here to everybody what near field means.
Situations where you see spherical wavefronts, for example.
Exactly. So I think this will naturally appear if we go up in frequency. I mean, the Fraunhofer's distance, if you go up to 100 gigahertz or even more, it's going to be, I mean, if you have tens of meters, and then for sure, if you're below, then the wavefront will be spherical. And what we have done so far in the context of line-of-sight communications is to assume as a channel model that we have a plane wave, which is, of course, not correct when you operate below the Fraunhofer distance. So I think this will naturally come.
Yeah, I just feel like we have to be very careful here when we speak of the near field, whether we mean the reactive near field of an antenna or the
radiative.
You want to say something?
Yes, I mean, we have to differ between those two. I mean, typically radiated near field, then you typically refer to, I mean, the magnetic fields around an antenna that we are typically not using, except when we are charging the wireless power transfer, then we are using that. But when we talk about the rays and spherical waves, and that is nothing new. I mean, we experienced that in massive MIMO already, but when we had our large arrays, and if you calculate I mean, what is the distance where you have a plane wave? If you have a long linear array with 128 elements, I mean, it's a kilometer away at some frequencies. So it's, I mean, it's already there today, those spherical near-field effects.
Yeah, if I can.
Yeah, and I mean, those have been there all along, as Fredrik said. So now we're speaking of being in the geometric near field or not of the array. And I think I remember that you and me gave a, I think, tutorial talk. Was it 2012 or 2011, 12, maybe 13? It's like 10 years ago. Wow. And you had this chart with measurements you had done with this linear antenna array. It was like 10 meters long, I think. And you show how these spherical wavefronts well, the impact of the fact that the wavefronts are spherical, and which obviously has to be taken into account. Maybe okay.
Yeah, I want to comment. So if we operate the digital domain, it doesn't make any difference to have a spherical planar. So I mean, in any massive MIMO communication system, the channel is spherical because it's the media channel.
Yeah, no, but that's such an important point. I think it deserves to be reinforced one more time, that as long as we operate in time division duplexing, relying on uplink pilots for channel estimation, then it simply doesn't matter whether we're in the geometric far field or geometric near field. We all rely on estimated channel responses for the decoding or for the beamforming, and then this becomes a moot point.
The big problem is that when you rely on a model, so for example, if you rely on the plane wave, then even if you have a digital or analog implementation, you can still use the plane wave model to point your beam. But if you operate in a near field, I mean, the phase array is no longer to be equally good as the digital implementation, because the channel is like that, and then you need to change the implementation of the system. Yeah.
Right, and I think what we have noticed now in this last conversation is also the difficulty with terminology here, because people have been studying these kind of effects all along, since as long as there have been wireless being researched as well, and we have been using different terms for the same kind of things, or roughly the same things here in the panel as well. So I think with that we should wrap up here and thank everyone who has been in the panel, everyone who has been staying with us here and listening in the room. So yeah, thank you very much.